Hello and welcome to Controllers Tech. In the past, we have covered a few videos on using STM32 Ethernet with the Mongoose networking library. In those videos, we learned how to integrate the Mongoose networking library with STM32, how to build different projects using it, and even how to perform OTA firmware updates through it. Recently, Mongoose has added some new features to their networking library, and I have decided to cover these additions in a few more videos in this series. So today, in part 5 of the Mongoose networking library series, we will focus on one of the newly introduced features, which is the real-time graph. This real-time graph feature can be used to display live, continuously changing data over a selected period of time. Using this graph, we can visualize data such as sensor readings, network throughput, CPU or memory usage, packet counts, voltage or current values, and many other time-varying parameters that need to be monitored in real time. In today's video, I will create 3 real-time graphs on the WebUI dashboard. 2 of these graphs will be used to display temperature and humidity data from the STM32 sensor, while the third graph will show ADC data from a potentiometer. Before we start working on the project, let's first take a quick look at the main features of the Mongoose library. Mongoose is a networking library for C and C++. It provides non-blocking, event-driven support for protocols like TCP, UDP, HTTP, WebSocket, and MQTT, making it suitable for connected devices. It has been available since 2004 and is used in many open source and commercial products, including systems used in space. Mongoose makes embedded network programming simple, reliable, and fast. The Mongoose wizard helps create professional web interfaces without needing front-end or design skills. It supports user login with different access levels, which can be enabled easily. Dashboards also show device connection status automatically. UI elements such as buttons, inputs, and drop-downs can be directly linked to C variables. It also supports firmware updates for microcontrollers like STM32 and ESP32 without extra setup. Let's open the Mongoose wizard and create a new project. Choose the option to create a new C++ project. Now select the project folder where you want all the generated files to be stored. Next, select the architecture you are working with. In my case, I am using the STM32H745 Discovery board. Set the build environment to Cube IDE, and keep the RTOS selection set to bare metal, since we are not using an RTOS here. Next, we will start with a completely blank dashboard and build everything step by step on our own. Here you can see our WebUI dashboard, which is completely empty at the moment. Let's go to the UI element tab and add a container. We will place all 3 graphs inside this container. Next, add a panel inside the container, and delete everything inside it, keeping only the text at the top of the panel. Now, let's change the title of this panel to temperature. Next, add a graph inside this last container, which means the graph will be placed inside the panel. Now let's duplicate this entire container 2 more times, so we can use them for humidity and ADC data. Also, make sure to rename the titles of these containers according to the data they will display. Next, we need to create the endpoints required for the graphs. Go to the REST API section and create a new endpoint. I will use the same endpoint for both temperature and humidity, since both values are read from the same sensor. Keep the endpoint type as data, which basically maps a C structure to this WebUI panel. The attributes act as members of this structure, where we will define the temperature and humidity variables. Since I want to display numeric values, the data type is set to double. Next, create one more endpoint specifically for the ADC data. This structure will contain a single element of integer type. Now that the endpoints have been created, let's go back to the page content section and assign the respective API variables to all the graphs we added. At this point, you can already see how the real-time graphs are going to look on the WebUI dashboard. We can further control the behavior of these graphs using the Graph Options section. If the graph options do not appear, simply refresh the page once. Now you should be able to see some data inside the Graph Options section. Let's understand what each of these parameters means. First, we have xRange, which is set to 30. This represents the time range in seconds for the x-axis, meaning the graph will only display data from the last 30 seconds. Next is update_ms, which defines the update interval of the graph in milliseconds. Currently, it is set to update every 25 milliseconds. After that, we have the scale option. Here, the y-axis range is configured from 0 to 100, and the graph will ignore any values that fall outside this range. For a temperature sensor, a more realistic setup would be to display data for the last 1 hour, with the graph updating every minute. However, for demonstration purposes, I will display the data for the last 5 minutes, with the graph updating every 1 second. I will also redefine the temperature range from 0 to 60 degrees Celsius. Let's copy this configuration and paste it into the graph options. Now go back to the REST API section and change the endpoint data type to array, and then change it back to data. Doing this forces the graph to update and apply the new graph options. You can now see that the temperature graph is updating more slowly compared to the other graphs. This is because it is updating every second, while the others are still updating every 25 milliseconds. We can apply a similar configuration to the humidity graph as well, but here we will change the y-axis scale from 0 to 100. Since humidity is measured in percentage, this range makes sense for displaying the data. For the ADC graph, I will keep the 30-second time range, but change the update interval to 100 milliseconds. Alright, the graphs have now been configured according to our requirements, so let's quickly test them. We will use WebSocket to update these graphs, and for that, here is a WebSocket simulator that you can use to test the graphs right away. To display the temperature data, we need to send the sensor endpoint name, followed by the temp attribute, and then the value. You can see that the temperature graph updates immediately with the value sent from the WebSocket simulator. In a similar way, we can send data to the ADC endpoint, and the corresponding graph will update based on the value sent. The WebSocket feature is not enabled by default, so we need to enable it from the settings section. That is all the configuration required on the dashboard side. Now click Generate to generate the project. If you plan to make changes to this project in the future, make sure to set the integration mode to integrate to existing project. This ensures that any changes made in the device project are not overwritten, and only the dashboard-related source files are updated. Alright, the project has been generated successfully, so let's navigate to the project folder. Here you can see that the complete Cube ID project has been created by the Mongoose dashboard. We just need to import this project into STM32 Cube ID to continue working with it. All the Mongoose-related files are placed inside a separate folder, which keeps them isolated from the main STM32 source files and helps maintain a clean project structure. Now let's open STM32 Cube IDE and import the generated project. This is the main file of the project. Before we move ahead with the code, let's first understand the hardware connections used in this setup. This is the schematic of the STM32H745 discovery board. The STM32 sensor communicates using the I2C protocol, so I will connect it to pins PD12 and PD13. I am also going to connect a potentiometer to pin PC0, which corresponds to ADC input channel 10. Now we need to configure these pins using CubeMX. Cube IDE no longer has CubeMX integrated, so we will open CubeMX as a separate application. Load the Mongoose project into CubeMX. In the meantime, let's build and test the generated project to make sure everything is working correctly. Open the serial console so we can view the log messages. You can see that the library has been initialized successfully, and DHCP has assigned an IP address to the device. Let's copy this IP address and enter it into the web browser. As you can see, the dashboard loads correctly, and the real-time graphs are running properly. Now let's move back to CubeMX and continue with the configuration. Search for pins PD12 and PD13, and configure them as I2C pins. These pins are associated with I2C4, so let's enable and configure I2C4. I am keeping the configuration at its default settings, where I2C operates in standard mode with the clock speed set to 100 kHz. Next, go to ADC1 and enable channel 10 in single-ended mode. I am leaving the ADC configuration at default, and you can see that pin PC0 is now configured as the ADC input. By default, the ADC resolution is set to 16 bits. Since we will read the ADC value in blocking mode, there is no need to change any additional settings here. There appears to be an issue with the clock configuration, so let's open the clock settings. The ADC clock frequency is above the maximum allowed limit, so we need to reduce it. Alright, everything is configured correctly now, so let's generate the project again. The project has been generated, so open Cube IDE once more. Now open the mongoose glue.c file inside the Mongoose folder. These functions are automatically generated by the Mongoose wizard and are responsible for sending and receiving data between the device and the WebUI. We should not modify these functions directly, because whenever the dashboard is updated, these functions will be overwritten by newly generated ones. Instead, we will copy these functions into the main file and then make small modifications there. By doing this, these functions will remain safe, even if we make changes later in the Mongoose dashboard and regenerate the project. Now we need to add the STM32 sensor library to the project. I have already covered a separate tutorial on interfacing the STM32 sensor with STM32, so I will reuse the library files from that project. First, let's download the project from the article. Open the downloaded project folder, then copy the STM32 C file into the src directory and the STM32 H file into the include directory of our current project. Next, include STM32 H inside the main file. We can use the STM32 init function to initialize the sensor, and then use the provided functions to read the temperature and humidity values. Inside the main function, make sure to initialize the STM32 sensor before initializing the Mongoose library. Now define the variables that will be used to store the temperature and humidity readings. Inside the sensor getter function, call the STM32 functions to read the temperature and humidity data from the sensor. After reading the values, store them inside the sensor structure so that they can be sent to the real-time graph. Let's also use mginfo to print the temperature and humidity values on the serial console for debugging purposes. Now let's build the project once. We can see that there are a few errors, so let's fix them one by one. The write function is already defined in the Mongoose generated project, so we need to remove it from the STM32 source file. Also remove the UART definition from the STM32 file, and make sure that the correct I2C instance is defined for the sensor. Alright, the project now builds successfully, so we can continue with the integration. Next, we will write the ADC getter function. In this function, we will first read the ADC value from the potentiometer, then convert that value into a percentage, and finally send it to the graph. I am creating a separate function to read and convert the ADC value. As mentioned earlier, the ADC is being read in blocking mode, which keeps the implementation simple and suitable for this demonstration. This map function will be used to convert the raw ADC value into a range of 0 to 100. Finally, the converted value will be returned by this function. Inside the ADC getter function, we will store this returned value into the ADC structure so it can be sent to the graph. At this stage, we have created custom getter functions for the graphs, but the Mongoose library does not recognize them yet. So, we need to register HTTP handlers for these functions. We also need to add a WebSocket reporter so that these functions are called periodically. Let's copy these registration functions into the main function, right after initializing the Mongoose library. The name of the handler must be exactly the same as the endpoint name defined in the dashboard. The getter function will be the one we just defined earlier in this file. I want the sensor data to update every 1 second, so I am defining this timing in the WebSocket reporter function. In a similar way, we will register the HTTP handler for the ADC data as well. For the ADC graph, I want the web server to update the value every 100 milliseconds. That is all we need to do at this stage, so let's build the project and flash it to the board. Here in the serial logs, you can see that the current temperature and humidity values are being printed. Now let's open the WebUI dashboard to see the updates on the graphs. The sensor graphs are updating every second, and you can view the exact temperature value by hovering over the graph. The time shown on the graph is in UTC, which you can also verify using the current UTC time. The ADC graph is updating every 100 milliseconds, so let's rotate the potentiometer now. You can see that the ADC graph responds immediately based on the movement of the potentiometer. This is how we can use the real-time graph feature to display both sensor data and ADC values. You can further extend this real-time graph functionality to build useful applications such as a heart rate monitor, an ECG waveform visualizer, or accelerometer-based motion tracking. With live plotting, it becomes much easier to observe trends, identify abnormal behavior, and debug sensors in real time, making it a powerful tool for both learning and practical embedded projects. We will use this graph feature again in the next video, where we will display live RAM usage on the WebUI. That brings us to the end of this video. You can download the complete project from the link provided in the video description. Leave a comment if you have any questions or doubts. Keep watching, and have a nice day ahead.